All right, welcome to Model, Eval, and Metrics Session 1. We just went through the course syllabus. We're going to go through now an overview of model evaluation, and we're going to talk through some mathematical notations. We're going to focus on a lot of formulas in this course, and we just want to refresh on how those formulas are represented shorthand notation. So we can read them as we're looking through documentation and reading new metrics that are coming out in the field of machine learning and AI. So we're going to talk about notation for actual versus predicted, and we're going to apply that to true positives, true negatives, and false negatives. These are the first four metrics that we're going to learn, and we're going to see how those metrics are combined to make up precision, recall, and accuracy. We're going to use those concepts and build on that to one of the cornerstone metrics in machine learning that's very much still used in ML and AI today, which is called the F1 score. So these are the foundations. These are important. They're simple concepts today, but they're foundations that I think warrant some deep understanding so that we can build confidently to that F1 score. So overview of model eval. So I'm just going to move these windows around a little bit here. I realized my previous screen popped up on the other window. Here we are. Let's talk about the purpose and the objective of model evaluation. So what is model evaluation? It's a process of assessing the performance of our machine learning models. In this course, we're going to stop using the word accuracy, and we're going to move towards using the terminology performance. Accuracy means something very particular, means something very specific. In machine learning, it's a metric that measures something in a mathematical formula for a metric that measures something in a particular way. And we don't always want to use accuracy. There can be many times where accuracy can be a poor metric to represent something. We'll talk about class imbalance, how when you're trying to work with a outcome that has a really small signal, a really small representation, such as fraud, trying to predict fraud, accuracy can make your model look like it's performing really well. For example, we're trying to predict fraud. Fraud is a rare event, and it happens 1% of the time. If we train a model that predicts that fraud actually never occurs, predicts 0 for every fraud event, we could have a performance of 99.9%. Now, if I tell you I have a model that has an accuracy of 99.9%, that might sound really, really good. But in reality, it's not doing anything that we intended it to. It's not finding any fraud at all. It's just predicting no fraud the entire time. And of course, that's why accuracy is a bad metric to tie to that problem. So in this course, we're going to find different ways of evaluating machine learning models so that we can determine the right metric to apply to the problem that we are facing. It's a really, really important part of machine learning. So why do we use true positives? I see a question. Why do we use true positives, false positives, true negatives, and false negatives versus true, not true, true, false, not false? Or is it all the same?
Sorry if that doesn't make sense. So true being like definitely true, right? We've proven it's true. Not true meaning it's definitely not true, but it might not be false. False being obviously it's 100% false, and not false meaning it's not false, but it might not also be true. Does that make sense?
It does. That's a good question. There are two types of situations that happen to a model outcome if we're thinking in this binary classification paradigm. The model can be correct or the model can be wrong, but it can be correct or it can be wrong in two different ways. It either said, yes, this individual has the disease, and they in fact did not have the disease, or it says, no, this individual did not have the disease, and in fact they did have the disease. So those are two different situations in which it can be wrong. So it can be wrong, and it's definitely wrong in both of those situations, but it's wrong in two different ways. One is a false positive, where it's saying, yep, they had the disease, but in fact they did not. It's falsely saying that they had the disease. And the other one is a false negative. It's saying, nope, they did not have the disease, but in fact they did. So it's falsely saying, nope, they're just fine, but in fact you will see them see their disease progress. On that same side, the model can be correct. It can certainly be correct, but it can be correct in two different ways. It either predicted one, yep, they have the disease, and it was correct that they did in fact have the disease, or it predicts zero. They did not have the disease, and it was in fact correct that they did not have the disease. So the true positive, true negative, false negative is really a paradigm to compare what did the model predict, what was the Y hat, versus what was the actual outcome. What was the why? What was the ground truth outcome of that situation? Does that help?
Yeah, I think so. I think I have a follow-up question, but I don't know how to say it in a good way yet, so I might just hold off.
You can say it we can work through it too.
I think it's just maybe like distracting because I think I understand the usefulness of the why of the true positive and the false positive. And what I think I'm trying to describe is a state that can't maybe necessarily like for example, if we assume that true false applies only to things that are extremely knowable, and there might be more vague states that are more common, right? Where we don't have enough information yet, and so the true state isn't necessarily true or false because those things require a great deal of evidence, versus sort of not true and not false, which hold the majority of weight, right? Like for some reason this isn't true, but we don't know why yet. Or for some reason this isn't false, but we don't know why yet. Like that seems to be like the norm of most stuffs. So that's my clunky way of saying it. And if this is like weird and not useful, we can pick it up later.
You point out a really good, I wish I had a slide for this, a really good point that's often missed when designing these predictive models, which is the delta of time between when the models make the prediction and when we can be confident about the ground truth of that outcome. So I'm going to try to whiteboard on this. Tell me if this is way off, but you have a process, and here this is time. We're going to have time along this axis, and we're trying to serve a prediction at this point in time, and we're saying we predict that this customer is going to stop being a customer with us. We predict that they're going to end their subscription service with us. But when do we predict they're going to end that subscription service? Is it in 30 days? Do we think they're going to end in a year? Do we think they're going to end in 2 years? The longer that we try to forecast that prediction out, the longer amount of time we have to wait before we assess whether or not that's true. So if we serve a prediction into production, we're going to have to wait 2 years before we know the outcome of this prediction and whether we were right or incorrect in that. Is that close to what you're You're alluding.
Yeah. Yes, for sure. Although I think you explained it like the mathy way, which was also useful. So thank you.
That's a very missed part in it. If we think life insurance, for example, actuaries have a challenging job of trying to predict how long people will live. And for any given individual that they're trying to build that prediction out on, we won't know the outcome of that prediction until somebody's lived their entire life experience. So it is a challenging problem that's often missed when we implement these models. So when we're talking about model evaluation, we are talking about the delta between what did you predict, this is our y hat, versus what was the ground truth outcome, the y. But there is work to be done here in the middle when you deploy your model uh, to make sure that it's performing in a way that you might expect. And I think that's more of what you guys will cover in the API class.
At a slightly larger level, there's also just like a certainty and uncertainty thing that I am thinking about a lot. And in particular, like I have this belief that we believe that the world is far more certain than it really is, and that a lot of the certainty comes from human systems that we've created, and really it is our creations that make certainty. Um, and so also part of it is about how do we know, how do we have certainty, and when do we have certainty? And I think it's very fleeting in terms of how long it's relevant. And so I think I'm like wanting to understand how to do this in like, math and machine learning, um, and I think I like understand it in a theory way. Uh, and so I'm also sort of just like grappling with that as you're talking.
There's a couple of implementations. Sorry, I'm supposed to say confidence. That I've seen for that. One is you hit on another really salient point. I think you're thinking beyond these basic concepts here, but one is the probability associated with these outcomes can be leveraged in a way to interpret some type of confidence about the model. So if it has a probability of 0.8, that's a higher degree of confidence than a probability of 0.7. We can interpret that as a higher degree of confidence that the outcome will occur. So I've seen probabilities, probability thresholds, confidence, and essentially when you get into the more of the LLM Gen AI space, log probs, leveraged as a metric for confidence in order to funnel down to those highly likely to be correct answers as we think about things like automation. When it's more sensitive that the answer has to be more certain, more correct, I've seen those metrics leveraged. The other thing I think you would actually really like, what we're talking about in this class is we're talking about kind of like discrete outcomes. But there's a whole realm of Bayesian. It seems like you think more like a Bayesian. And there's a wide set of tools that help us build model outputs that are representative of trials, not just we're going to have an infinite amount of time to run these trials, but let's update our outcomes based on our experiment that we've run through the different trials and update the probability distributions associated with that at a trial level. So I think these methodologies are going to lean a lot closer to what you're looking for there. I found this particularly useful. There's one use case I actually use this in where they wanted to send a series of letters across groups of people but they wanted different people to have customized experiences. So based on your, maybe you want to receive all your letters at one point in time because you just want to check all the boxes and be done. Somebody else, that's overwhelming for them. They don't want that type of experience. They just want to receive a letter every month and have it be really scheduled cadence so they can take their time doing that. They're not overwhelmed with this huge packet. And the campaign was over 90 days. And we found that in order to use traditional techniques to have enough evidence to say, yep, this is definitely the right pattern to mail this individual, we would have had to run experiments until the sun exploded. And we realized that just a linear combination of being able to do that, the search space was way too large. And so we leveraged a Bayesian technique actually instead to update our belief about the world based on trials and experiments. Good questions. That was really deep for our intro slide, so I apologize. Thank you guys for going deep into that with us. Why are we doing this? Why even evaluate these models? Why even explore these techniques, these building confidence around these predictions? It's because it helps us determine how well the model generalizes to unseen data. So that's the key word here. This is the main goal of us building machine learning models. We want our models to generalize to unseen data that meets whatever we set as our desired objective. So we don't just want a model that performs well on one niche particular data set. If we're making a music recommendation model, we want a model that performs well generally for all music listeners and their content of recommendation. We don't want it to just perform well on our training set. So we're going to leverage methodology that helps us not do things like data snooping or essentially impair our model's ability to have that generalized capability. What this allows us to do is it allows us to systematically, to scientifically compare different models and select the most appropriate model in a way that is quantifiable and defendable, that it is the best model because of these methodologies that we've employed. In order to do that, we have to first start with some mathematical notation. So we're just going to go through functions, notation, some quick terminology. As you guys navigate the space, the goal is to give you the tools to learn more about AI, learn more about machine learning on your own. And just a quick review of these things can help you read and parse that information. So we want to represent the way that we measure these things, the algorithms, in concise ways. If you remember, we talked about functions. Functions take input and they produce output. So we have this f of x. F of x is our function and x is the input that it's going to take. And then what's being applied to x is we are squaring that x value. And that's what we're outputting. Similarly, we're going to use, so we're going to talk about everything as functions now. When we talk about accuracy, we're going to talk about accuracy as a function. So we're going to apply accuracy to a set of data. We're going to apply precision and recall. All of these metrics that we're applying are functions. So in this case, in this example, we have f, just to be very verbose about this, we have f of x. And f of x is represented here. It's representative of 2x minus 2. So f of x and 2x minus 2 are the same things. We can use them in an interconnected way. So if we say f at negative 5 takes the value of x in our function, and then you can evaluate that to an actual outcome. So if we have f of 5 in here, it would be 2 times 5 minus 2. We already worked with functions in our y equals mx plus b. Our linear formula here, we can change that to be f of x equals mx plus b, and then we can pass x to this linear function form, and it can be, and we can generally apply that. So our methods here that we learned in this previous class, linear regression, logistic regression, neural networks, and decision trees, these can also be represented as functions. So we're going to evaluate these functions. And oftentimes what we're going to use to do that are these summation functions. If you guys remember, the reason we talked about functions is because that's what's going to be represented here, typically in that summation term. Let's walk through an example here. So a summation function is going to be denoted by this symbol, and we're going to apply some operation to all the values in our data set. For example, we have 4n here, and we're going from n equals 1 to 6. So this summation example would iterate over all of these values. So it would do 4 times 1, because this is our start. This is our stop. And this is our function. So we have 4 times 1. You guys remember the summation function is just going to add these together. It's 4. 4 times 2. 8. 4 times 3. Etc. all the way down 4 times 6. And then we would add the value of all these together. Does that make sense? You guys remember summation functions? Okay. Here's a better example here. So if f of n is our function and we're moving from 1 to 4, it would be f of 1, f of 2 plus f of 3 plus f of 4. So in this case, we're doing our f of n is equal to n plus 1. So it's 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1. So the outcome of that is 14. The other notation that we're going to use is predicted versus actual. So we talked about this just a little bit already. So this is going to be our y hat versus our y. So we're going to, in the context of evaluating our machine learning models, we're going to represent what did the model predict versus what's the ground truth, what happened in reality. There are two notations we're going to use to do that. One is going to be y hat. It's represented as this. When I typed it into a slide, it's poorly represented as next to it. But these are the predicted values. These are the probabilities from your model, the outputs, the estimations of your machine learning model. This is what it tells you is going to happen in the future. So these are generated by applying your machine learning model. We're predicting the price for a house. This is the predicted price from your machine learning model. You go online to Zillow and you look at their Zestimate online. That's your y hat. That's your predicted outcome. Of course, as you guys remember, in regression problems, these predicted values are continuous numerical outputs, and in classification problems, these are class labels. The actual outcome, the ground truth, reality is our y variable. So the actual outcomes and true values, we're going to compare y hat versus y. So these are the known values, the outcome After we talked about the implementation where it took 2 years to actually measure, this is the outcome after 2 years. Or in our house example, this is the price that a house actually sold for. This is who actually survived the Titanic in your Titanic problem, or the actual classification of a flower in your iris data set. So our predicted values, we're going to represent these as an array of values here, our y hat, and our actual values are going to be represented as y. They are the same measurement, so they're both going to be house prices. If you have a house price problem, they're represented as the same data structure, but they are measuring what did your model predict versus what's the actual outcome. This is what enables us to evaluate the accuracy, the precision, the recall, and all the metrics that we're going to work with in this course. Okay, so in order to talk about true positive, true negative, false negative, we first need to talk about positive instance. And I know we've been going for an hour, and this seems like a natural stopping point. So let's come back in 10 minutes.
Yeah.
You,
That was a lot of fish.
okay, you can put it in the kitchen. You ate all those fish sticks?
Yeah.
Awesome job,
Every
bud.
single one. Just this one has one left.
That's fine. You did amazing,
You
bud.
could finish it.
No, I still have my own food, silly. But you can leave it in the kitchen and we'll take care of it.
Fish stick sounds great.
Yeah, I could go for some fish sticks. My
Oh,
parents
wow.
are
I
like,
thought I was muted.
You're such a good parent.
my parents are on vacation. They usually leave me food, and driving to my parents. I'm like, oh crap, I'm not gonna eat dinner today.
I need to get Charlie more into fish sticks. That's it. That's a good introduction into fish. We don't get a lot of that as a landlocked state.
I need to get my oldest into other than chicken nuggets and quesadillas and noodles. He loves ramen noodles. That's it.
Ramen noodles, yes. That's awesome. Okay, positive instances. In the context of machine learning, positive instances are when they belong to our category or our class of interest. So they're the positive label for the problem that's being solved. So this is important because I think if this gets flipped, it gets confusing. So if we are trying to predict fraud, for example, hey, this is a common problem. Many companies try to predict fraud. If you have a credit card, I just went on a trip to Florida and I started using my card in Florida, and my company shut it off because they said this seems unusual. And they send you a text now and say, hey, this seems unusual. Is this a real charge? And you confirm or deny. So that got flagged as fraud. Now, fraud, the percentage of fraud that occurs is usually a really small percentage compared to all the things that happen, the regular purchases that every single person makes every day that are not fraud. So maybe this is like 0.2% or something to that effect. I don't actually know how much it is. And perhaps this 99.8% of the time purchases are made, they are not fraudulent purchases on a card. 99.8% of card transactions are not fraudulent. So in this case, when we're training a model and we want a model to predict fraud, we're applying these labels, these zeros and ones. Remember when we had to transform our data into our numerical information into zeros and ones. So we have our target. Was it fraud? And maybe this says FR fraud. And maybe this says not fraud. We have to transform those into zeros and ones in order for our model to understand, to make these predictions. When we apply these predictions, fraud will always take the value of 1, and the other instances will take the value of 0. So in this case, our positive instance is fraud. We're trying to predict the probability of fraud. Do not label your instances of not fraud as ones, is what I'm saying. This is true for whatever outcome that you are trying to predict. You're trying to predict what is the likelihood that somebody has a disease. Then you should label the disease outcome patients as 1 and the other patients as 0. If you are trying to predict what is the likelihood that a customer will convert, you should label the customers who converted in the past as 1, the other outcomes as 0. If you're trying to predict the likelihood that this email is spam, the spam emails get labeled as 1, the others as 0s. The zeros are our negative instances. So these represent when that class or that instance, that outcome did not occur. The outcome did not occur. These are the opposite occurrence of our positive class. So positive class represents true, represents 1. In our case, it's the spam outcome. And our negative class represents false or represents 0. In binary classification, we typically have 2 classes, as you guys know. We have our class 1 instance and our class 2 instance, class 1 being the positive outcome and class 2 being the negative outcome. When we look at multi-class classification, it gets a little different. So we have more than 2 classes. Maybe we're trying to predict images. For example, our handwritten image example, we can have images represented as instance 3, images represented as instance 7. We can turn these into a binary classification problem by saying, is it image 3? Does it represent an instance of image 3? Yes or no. Does it represent an instance of image 7? Yes or no. Imbalanced data, we already started using this terminology. So here's the definition for it, is when the data set is not very equally distributed between classes. So if we look at our fraud example, I'm just going to go back on slides instead of trying to rewrite. If we look at our fraud example, this is some heavy class imbalance because only 0.2% represents class 1 and 99.8% represents class 2. Our model is going to have a hard time trying to find this signal because it's not represented as a very equal representation. There's a heavy class imbalance, an imbalance between class 1, which is fraud, and class 2, which is not fraud. If we look at disease prediction, there's often a class imbalance between disease prediction. If we look at conversion rate, there's often class imbalances between conversion rate. The reason imbalanced data, imbalanced classes are important is because it may change what performance metric that you choose. So we'll look at accuracy, we'll go through the measurement of accuracy and see that how it can be manipulated to represent a metric for things with heavy class imbalance, such as fraud. So it requires careful consideration when working with classes that are really imbalanced. Now, this doesn't just apply to binary classes. You can have heavy class imbalance across multi-class classification as well. So if we look at our images of image labeling, say we have images that are 1, images that are 2, images that are 3. Remember, we had the handwritten 1s, the handwritten 2s, the handwritten 3s. We have a data set here, and I'll even put one more. Maybe 1s represent 10% of our data set. Maybe 2s represent 20% of our data set. Maybe this also represents 20% of our data set. And maybe 4s represent 50% of our data set for some reason. There's some heavy class imbalance here. There's this 10% of our data set is really small. So 1 is really underrepresented. It's imbalanced in our class representation across this multi-class classification that has 4 labels associated with it. So this concept of imbalanced data, class imbalance, broadcast to multi-class as well. Okay, so I think that's about it for overview, kind of bridging those last 2 weeks from the previous course. Now we're going to dive into the first topic of the new content to you guys here, which is true positives. We're going to use true positives, false positives, true negatives, and false negatives to build our understanding of how precision and recall work, which are 2 metrics that are used to combine together for something called an F1 score, which will then generalize to an F beta score. So this is the path we're going on here. True positives, these represent the instances that are correctly classified as belonging to the correct class. So we have, and each of these will do a Y hat. and we'll do a Y, the real ground truth outcome. So true positives are the instances when we said it was 1 and it was actually 1. So we predicted that it was spam and it was actually spam. We predicted that the individual would survive the Titanic, and they actually did survive the Titanic. So these are when both the actual class and the predicted class are positive. In this case, this is when we were correct. This is one of the situations. Remember I said there's 2 situations in which we're correct, 2 situations in which we're wrong. This is a situation in which we are correct. Then we have false positives. So we can predict 1 and our machine predicted 1 and it was actually 1. We can also have our machine predict 1. We have y hat is 1. But in reality, it was actually 0. So false positives represent instances in which we incorrectly classified the positive class when in fact it did not occur. So we were incorrect. In false positives, we are incorrect. We said that an individual would survive the Titanic. In fact, they did not survive the Titanic. We said that they would had markers for this disease. In fact, they did not have markers for that disease. So the false positives, we falsely predicted a positive prediction. True negatives. So this is another situation in which we are actually correct. In our matrix here, we have y hat and we have y. And this is when we predicted 0 and the outcome was actually 0. So true negatives represent instances that were correctly predicted as belonging to our negative class. So we have this is where we said it was not spam and it in fact was not spam. In a lot of cases, especially class imbalance, we actually don't care about this. We actually don't care when we say it's not spam and in fact was not spam. We are less concerned about the times when we said, yep, they don't have the disease, and they in fact did not have the disease. I'm not saying this is always the case. You have to look at your situation. But when we look at something called the F1 score, we'll see that it actually doesn't take the true negatives into account. So it does not emphasize any weight on this because it's less important to our outcome. The last one here of our set of four outcomes for our little matrix here is false negatives. So in this case, we falsely said that it was negative. Does anybody know what our y hat would be here? Go ahead there, Luke, give a stat on it.
Is it 0?
It is 0. So we predicted 0. What was the actual outcome?
1.
The actual outcome was 1. So we falsely said that it was negative. Our model said 0. In reality, it was 1. So these instances are classified as belonging to the negative class, but in fact, they belong to the positive class. So we said, nope, this individual does not have the disease, but in fact, they do. All right, here's kind of a overview of this. So we can use this to construct something called a confusion matrix, where you can represent, we can actually put numbers to these and give a really quick look at this. And we'll continue looking and working with confusion matrix and matrices next time. But here's a summary of everything that we talked about: true positive, false positive, true negative, false negative. So true negative, it's when we predicted that it was negative, but in reality, it was also actually negative. So these two blue squares are the times in which we are correct. The true positives are when we predicted it was positive and it was actually positive. Remember, I said there's two situations in which we're correct. We said it was negative, it was actually negative. We said it was positive, and it's actually positive. There's two situations in which we're wrong. That's when we predict a positive instance that was actually 0, or when we predict a 0 instance that was actually 1. So we predict a 0 instance that was actually 1, or we predict a positive instance that was actually negative. Predicted negative and it was negative. Predicted positive and it was positive. All right, this is a moment to pause. How's this sitting with you guys?
I mean, it all makes sense.
Excellent.
And it feels like, I don't know, back in biology, talking about genetics, X and Y, and the diagrams that follow.
Absolutely. Yeah, it's kind of like a Punnett square, isn't it? Yep. That's exactly it. And here's a fun analogy here for you guys. If we're thinking about you trained a model and you gave it some images, and your model's goal is to predict if this picture is a hot dog or not, if there's a hot dog in the picture. Well, let's look at the two instances in which the model is correct. Well, the model is correct if it says, nope, it's not a hot dog. It predicted 0. And it, in fact, nope, that's pizza, so it's not a hot dog. Is not a hot dog. There's probably a lot of situations, a lot of pictures that are not hot dogs where it says, nope, it's not a hot dog. And that's why I said there's typically, from a metric evaluation perspective, we care a little bit less about true negatives. True positives, on the other hand, these are the situations when our model made a correct positive prediction. We said 1, it's a hot dog, and it said, yep, in reality, that's iconic hot dog. That is a hot dog. There are two situations in which our model is incorrect. One where it said it's a false positive. It said this looks exactly like a hot dog. In fact, it is not a hot dog. It's a dog wearing a hot dog costume. So that would be a false positive. This is like a false alarm. The boy who cried wolf here on models. This is called over-predicting. You guys are curious? We are over-predicting. We have an overexcited model, essentially. And this is called under-predicting. Sorry, that's supposed to be you. I can't write on here. You guys know that by now. I'm gonna get an iPad. That's what I've decided. Actually, I have an iPad for my 2-year-old. I just need to hook it up to this. Use it for more than 2-year-old Khan Academy. So false negative is the situation when we're wrong. In this case, we said this is not a hot dog. In fact, it is a hot dog. It's just a chili dog. It looks a little different. It's a picture that looks a little different. We probably didn't have enough examples of chili dog in our training data set. It was probably something called an underrepresented sample. And we probably need to apply some type of technique, such as oversampling, to represent this stronger. This is really important because we see this quite a bit. I'm a big proponent of do not use AI to review resumes, for example, because I think there are a lot of individuals who are underrepresented in the candidate pool for resumes and for job applications and for conversion into those roles. And I think AI, well, we know that machine learning can learn from the majority of data. And if there are things that look different and are underrepresented in the data, such as our chili dog here, our model can have high degrees of false negatives on those underrepresented samples. So these metrics are important because it helps us understand how machine learning and how AI works and how to evaluate it and point out these problems and inconsistencies. Okay, exercise for you guys. Can you calculate the true positives here? So given this data, here's what our data looks like. We have a binary classification model predicting 1 or 0. Here's what our model predicted. This is our y hat. And this is our y. Can you guys calculate the true positives, the false positives, the true negatives, and the false negatives?
So just comparing top down, there's 2 true positives. Or wait. So true positive would be double ones, right?
True positive would be double ones, correct?
Yep. So we have 2 of those at 0 and 3.
Perfect. 0 and 3. So this is our 0 and 3. 2 true positives out of how many?
6 total.
6. Let's simplify that. 1/3. So this is TP. Well, I may not be able to label all these. All right. What's next?
A false positive would be a 1, 0. So just at 1, right?
1, 0. Which position?
Position 1.
Position 1. Perfect. And this is our false positive.
And that make it 1 out of 6.
1 out of 6. Oops. Here we are.
And a true negative would be the inverse, so 0, 1 at position 5 and position 2.
True negative is when we predicted it was negative and it was actually negative.
Oh, true. Oh, okay. I got ahead of myself. So that would be position 4, the 0, 0.
You got it. This is 0, 0. Position 4. 6. And last one.
Then the false negative just leaves position 2 and position 5.
Oops, I forgot to label this. FN, TN, N. So this was R01. This is Y hat. This is Y. And we had 2 of those, 2x6. And this is 1/3. All right. The sum of these, by the way, should add to 1.
Oh, they're all part of the whole, so yeah.
If you put it in a percentage, yeah.
Okay.
So these should all add to 1. True positives plus false positives plus true negatives to false negatives should always add to 1. Great. I think we have this written on the slide as well. Oh, no, this is the summary. I thought I had an answer slide after that. I do not. This is just the summary here. So important things to keep in mind moving forward from this. We did a lot of refresher on stuff, but the Y and Y hat, so we started using that quite a bit, the Y and the Y hat. The other thing I didn't touch on, but maybe should have, when we say Y subscript I, that means Y at the I data point. So if we have a table here and whether or not people survived the Titanic, we have person 1, person 2, person 3, person 4. We're 0-based indexers. Person 0. When I say Y at 2, that's if it's 0-based index, that's going to represent this individual. If I say Y at 0, that's going to represent this individual as well. So Y at I represents a given particular instance that we're looking at. Summation notation, We quickly reviewed that. P is the positive instances and N is the negative instances. And now you guys know true positive, false positive, true negatives, and false negatives, which are very useful foundational terms for all of machine learning, data science, AI, very relevant. So let's do an intro to performance metrics for classification problems. So notice as we were talking about, let me do a time check here. Oh, we're doing really good. Okay. So I think this is the last section I have in here, by the way. So we will, we got quite a few slides though. So we see, and we've got 2 breakouts. Actually, one of them's the summation function one, so maybe we should do that one. Let's do our summation function breakout here real quick. Let me stop sharing so I can share that screen. One moment just to get to. Let's try to, let's just play with some Python code here for just a minute. Let's build a summation function. So the summation function takes 3 parameters here: the start of the summation, the end, and a term function. So with our function that we're passing to this. So I think in our example, we had 4 times I. So inside the summation function, it loops, then applies that function and sums the results. Here is the function here. So if we have I to the power of 2 and Python star is to the power of, we define that as our term function. And we apply from 1 to 5, we get this result. So try, let's validate what we did earlier. It was 4n. So try to implement this for 4n. For n, n equals 1, and the stop is equal to 6. Spend about 5 minutes on that. Okay. What did you guys do for this? Does anyone want to volunteer as tribute? There we go. Thanks, Luke. Let's do that. Term function. Just 1 second. We're going to return 4 times I. Show results equal summation and I don't know why. Oh, indentation here. Oh, depth. There we go, 84. So we have a term function. We created a new term function. We're overwriting this one now, and instead we're saying 4 times I. We're passing that term function, starting position, ending position, and producing the results. Okay. Let's jump back to our slides. And take us to where we were. All right, performance metrics for classification problems. So notice when we were talking about true positive, true negative, false negatives, we didn't talk about our house problem, our regression problem, our standard regression problem. We didn't say use those metrics, true positive, true negative, false negative, to evaluate how well we predicted the house price, for example. So different performance metrics you're going to want to leverage for different types of machine learning problems. That's why we have these bucketed, one of the reasons we have these bucketed into classification, into regression. So here's performance metrics. We're continuing to build on these performance metrics for classification. So accuracy is a classification problem metric. We typically don't refer to accuracy for regression tasks. So accuracy is a great metric because it's really intuitive to everybody. When you say, what was the accuracy of your model? What was the accuracy of your prediction? It's very intuitive for us to understand. And because it measures the proportion of correctly classified instances. So measures the proportion of correctly classified instances. How often were we correct? It's a very natural way of thinking about the problem. It just quantifies how often the model made correct predictions. So to measure accuracy, we just, in our formula, our mathematical notation, really structured mathematical notation here, we just say how many correct predictions did we make out of total predictions. So how often, this is a little slow, there we are. How often were we correct over all predictions that we ever made? Let's put this into the context of what we've been talking about. True positives, true negatives, and false negatives. When we think about the number of correct predictions, remember we said we could be correct in 2 ways. We can either predict true positive, or we can predict true negatives. We predicted 1 and it was actually 1. We predicted 0 and it was actually 0. So true positives and true negatives. When we say the correct predictions over all predictions, we have to consider all the ways in which we were correct. So the true positives and the true negatives. And the 2 ways in which we were incorrect, the false positives and the false negatives. So accuracy is true positives plus true negatives over true positives plus true negatives plus false positives plus false negatives. So what I think is really cool about the confusion matrix that we were looking at, when we put actual numbers on this, in your head, you can actually calculate the accuracy. I think this is really neat, really powerful piece of a confusion matrix. And I'll probably tell this story again the same time when we talk about this next week. But one time I was giving I was early in my career and I was giving a presentation to a leader on a model that I had trained. And I said, hey, here's the accuracy for that model, 85% or whatever it was. And I said, here's the confusion matrix for that model. And the individual was very quick on the spot, and I really respect their leadership. And they said, that doesn't make sense. Your confusion matrix doesn't match your accuracy. And I said, oh, I'm certain it does. I'm certain it does. And I had to really think about this for a second. And I went back and I looked at the code, and they were right. My confusion matrix I had produced on the test set, and accuracy I had produced on the overall data set, all of the data combined. So they were actually metrics that were measured at different levels of fidelity, two different data sets, essentially, which we'll talk about methodology and how to avoid such things. But it was, you can calculate accuracy and these other metrics, precision, recall, and F1, just by looking at a confusion matrix. So that's why it's important to know how these true positives, true negatives, and these other metrics combine. So let's do an example here. Can you guys calculate the accuracy? So suppose we have a binary classification problem and we're predicting spam. We'll do a lot of spam examples here. And so spam is, of course, our positive class. We have a data set of 100 emails, and out of 85 correctly classified emails, 50 are true positives and 35 are true negatives. What is the accuracy?
%85%.
85%, you got it. So we can do it a couple of ways here. We have 85 correctly classified emails. Oops, sorry if my pen is bad. So we have 85 that we know are correct predictions. And we said the data set had 100 email samples, so we could do 85 over 100, which is 85. Or we can add our true positives and our true negatives. We can do TP plus TN over our 100. And that's 50 plus 35, which is, of course, 85. Okay, pretty simple example, but we're going to do these types of examples for each of the metrics to kind of ground them home. So we're going to start with accuracy here. Like I said, great metric because it's very intuitive to people. They understand what accuracy, anybody you speak with, even outside of your data science expertise, understand what accuracy is. It's a really simple calculation. It's pretty comprehensive in terms of coverage on the data set, but be careful with it because it's very sensitive to imbalanced data sets. It tends to reward the largest class is what it does. The greatest representation gets the highest credit. And it's very insensitive to misclassification costs. So when we're looking at when we're looking at situations where the cost of being wrong is high. So disease prediction, or our fraud example, if the cost of being wrong is high, then accuracy is not a great metric. And as we see and explore other metrics, to your point, Luke, about confidence, accuracy does not capture prediction confidence. And we'll see as we build, there's other metrics that can help us actually quantify confidence of the prediction. Precision is the proportion of true predictions among all positive predictions. So this is our first metric that is maybe new to you guys. Precision is, so here we have true positives over true positives plus false positives. So out of all of the times that our model predicted a positive instance, how many times were we actually correct? So you can think about this as, out of all of the times that we told somebody that they had a disease prognosis, how many times did they actually have that disease prognosis? How precise are we? Out of all of the times that we predicted spam, whenever our model has ever said that it was spam, how many times was it actually spam? So true positives are one of the situations in which we are correct. And then we also want to measure the false positives, when we said it was a positive prediction, but it was in fact not. Any questions on precision? Precision is measuring the quality of our positive predictions, the quality of our signal that our model is producing. Oh, I guess this is on the next slide. There we go. The quality of our positive predictions made by the classification model. So the proportion of correctly predicted positive instances, true positives, out of all the times that the model says, yep, this for sure is going to occur. It's particularly important when the cost of a false positive is high. So when do we need high precision? We need high precision when the cost of a false positive is high. So in the disease prognosis example, the cost of telling someone that they have a very serious disease outcome when they in fact do not have that disease outcome, that's something that we want to measure with precision. How often are we communicating bad news to people when in fact we don't need to be causing that trauma and that stress to them? This is precision. A high precision indicates our model will make very few false positive predictions. Very, very, very few times it will incorrectly say that it's a positive instance, that it's likely to occur. In fact, it doesn't occur at all. So as you guys think about, when I say what types of predictions are not considered in the precision metric? So when we say TP, FP, TNFN, check to see if you guys are listening here. Which of these is not considered? Which of these types are not considered in precision?
Anything with a negative, true negative, false negative?
Yep. True negatives and false negatives. Let me confirm. Yep. True negatives and false negatives. So when we are predicting 0 and it's actually 0, remember I said we don't really care quite as much about those in many incidences, but we're also not concerned about false negatives in this metric. So situations where we say it's 0, but it's in fact 1. So instances, we'll do this in the next example actually. Here, can you calculate the precision? So we have our email spam problem again. Out of 100 emails, our model predicts that 50 of those emails are spam. Can you guys calculate the precision here given this information?
Would the precision be 80%?
That is correct. So we have our precision is the true positives over true positives plus false positives. So we had 40 for our true positives, which again is 40 over plus 10. So we had 10 false positives. That's 40 over 50, which is 80%. The partner metric to recall, or the partner metric to precision, is recall. So in precision, remember we looked at true positives over true positives plus false positives. In recall, we're looking at true positives over true positives plus, now it's false negatives. So when were we correct? Over all of the situations in which we should have been correct. So out of all of the instances of individuals having that disease, how many of them did we identify? So if in a population, 20% of people have that disease, what percentage did we find in our model? Did we find all 20% or did we only find 10%? So you can have a very high precision, but a low recall. And you can have a high recall, but a low precision. So these metrics, they sort of trade off with each other. Recall has several different names, just so you guys know for awareness as you're learning on the internet. It's also sometimes called sensitivity. It's also sometimes called the true positive rate. I typically tend to call it recall. And it's used to assess the completeness of our positive prediction. So how much of the population that actually has that outcome did we find? And it's a very important metric. Again, I'm going to use the disease example because I think it kind of hits home with precision and recall. Let's imagine we're trying to predict the outcome of a disease, or that an individual has this disease, and we tell them that they in fact do not have the disease, but really they do. That's what recall is measuring. Recall is measuring how often are you telling someone that they do not have the disease, but in fact they do. So it's the proportion of correctly predicted positive predictions out of all positive instances that exist within the data set. So it gives our model the ability to minimize. If we optimize recall, it gives our model the ability to minimize the number of false negative predictions. So it's important when the trade-off of telling somebody that they don't have that outcome when in fact they do is very high. So maybe for medical diagnostics and medical diagnoses, if they continue to, that disease can get much worse without treatment. So it can have really severe consequences. A high recall indicates that the model is really effective at identifying a large portion of the positive instances that exist in the data set, that exist in the world. It means it's capturing quite a bit of the signal. A low recall means that the model may miss a lot of these positive instances, and it can lead to a high number of false negatives. So let me talk about one more thing here on precision and recall. These things aren't necessarily bad. We can control precision and recall in situations where we want to. I think you guys have heard me say this example, but let's say we have this. You can use these metrics to talk with your stakeholders. Let's say we have this document and it's this contract, and people can come in and make changes to this contract. So at some point in time, somebody makes a comment on this contract. And now we need to know which of 9 teams downstream need to take action on this. Is this team 1? Is this team 2? Is this team 3? And we faced a problem, which is we're dealing with the trade-off between precision and recall. And the question was, do we over notify people? Do we tell people too many times that they need to take action on this document? Essentially, do we have a high recall? High recall would be over notifying people. Or do we have a high precision and basically just notify people when we're really, really sure that they need to take action on this document? And this was a choice that we were able to put into our decision makers' hands. And they told us, no, please have a higher recall. If somebody over notify us, that way we have all of the eyes on it. We'd prefer to make that trade-off as opposed to under notifying us and only notifying us when we need to. So there's pros and cons of both, but they're just trade-offs that we can make. Okay, can you calculate recall? Here we have 100 patients. We're talking about our disease outcome example here. 60 of the patients actually have the disease, and the model correctly identified 45 of them as positive. What do you guys have for recall here?
Is it 25%?
75%. So we have,
so the opposite of what I got. Gotcha.
yes, I think you flipped the 15.
Yeah.
The 45 of them are positive, so we have the 45 over the 45 plus 15. So the only difference between recall and precision is this part right here. So they both do true positives over true positives plus precision does false positives. And recall does true positives over true positives plus recall does false negatives. So one does false positives, the other does false negatives. Another useful way just to ground this same topic, I know I'm kind of, we're overdoing it with precision, recall, true positives, false negatives. But like I said, this course, we go deep, we really ground in this understanding. I hope this, you guys feel very confident in these things and you can take these metrics back to the work that you're doing and you can assess with confidence the true positives, false positives, true negatives, and false negatives. This is a very, very heavily used terminology, foundational terminology in the field that builds to other metrics. Here's a different way of thinking about the same thing. I really appreciate this visual. I think this is something that maybe resonates more with you, Luke. I think some people are more visual about these things as opposed to notational. If we look at this circle here, this circle that says selected elements, this is our model. This is our f of x in terms of model predictions, not our evaluation formula, but this is what our model is trying to predict. And there are times when the model is correct and there are times when the model is wrong. If we look at this, if we look at this left pane here, this green pane, where it says relevant elements, these represent all of the positive instances. So all the circles that are filled in are all the positive instances of the world. So there are times when our model predicts positive and it's actually positive. This is this slice of the pie. Our model predicts positive, it's actually positive. And there are times when our model predicts negative, but in reality, it's positive. There are times, and then this other pane over here represents all of the not span instances, all of the 0 instances. So this relevant elements represents all of this whole pane represents all of the 1s. And then the circle is when our model predicted 1. Outside of the circle is when our model predicted 0. So for true negatives, these false positives, this is when our model predicted 1, but in fact it was 0. So our model predicted 1, in fact it was 0. Our model predicted 0, in fact it was 0. This is when we're correct. This is when we're wrong. True positives, we're correct. 1, 1. False negatives, we predicted 0 was in fact 1, and we're incorrect. So just a different way of looking at it. If you're thinking about it from this picture, you can imagine precision like this. This is precision. How many times did we predict, did we have correct positive predictions? All of the positive predictions. So all the times that we predicted positive, this circular element here. You can think of recall in this way. All of our positive predictions over all of the positive elements that exist within the data set. So all of our positive predictions, how many did we capture? Look at how many exist in this data set. Did we capture all of them? And precision is when we did make a positive prediction, how good were we? All right, does this visual representation help ground this a little bit? Okay, excellent. I thought that would resonate with you, Luke. Here's extra resources, by the way. I pulled all these pictures from this site here, and I found their explanation of precision, recall, and accuracy quite good. I think we have one more breakout exercise today, and then we will actually be done. So let me open that up. Let's go ahead and open up the accuracy notebook. Let's calculate some accuracy. Let's use true positive, false positive, true negative, false negatives. Did we already do this in the other class? I feel like I'm having deja vu here. No? Okay, I hope not. Somebody tell me if we did. Let's use this to actually create our own accuracy function. Let's define a calculate confusion matrix, and let's break it into true positive, false positive, true negative, false negatives. We have a y true and a y pred. Y pred is our y hat. Y true is just our y. This is a notation we're going to switch to. I should add that to the slides. Y pred is our y hat, and y true is our y. From here, we're going to calculate our confusion matrix. So based on this, I want you to implement your own accuracy function. But I want you to calculate accuracy using true positive, false positive, true negative, and false negative. So I give you something that's going to calculate your TP, FP, TN, FN for you. Use those values and implement that in an accuracy function and calculate the accuracy. Let's spend 5 minutes. All right, does anybody have a snippet they want to share? Awesome. Accuracy. We're going to define as, we're going to create a function. We're going to call it accuracy. It's going to take in two parameters. It's going to take in y true and y pred. Inside of this function, we're going to get the true positives, the false positives, the true negatives, and the false negatives by calling our confusion matrix. And we're passing in those two parameters, our y true and our y pred. We're going to calculate accuracy as the true positives plus the true negatives over true positives plus true negatives plus false negatives, and we're going to return the accuracy. So didn't slide here. There we are. Let's call this. I have to run the cell first. And I should have spun up my compute. Here we are. Invalid syntax. Oh, here we are. Y true. I didn't define that here. There we are. And 0.5. So in this case, we had an accuracy of 0.5. So this is a really straightforward implementation. Just wanted to show you guys how the code that we're going to work with. The benefit is sklearn has all these metrics for us. So if we look at sklearn accuracy score, fantastic thing about working with sklearn is they have all of these metrics implemented for us. So we'll actually import. We won't have to build our own precision or our own recall score. We can actually, from sklearn, import accuracy score, and we're going to call their accuracy score on our y true, our y pred. There's a reason I made you call that y true, y pred. And we can see that, way to go, Luke, you implemented a function that actually has the same accuracy outcome as sklearn. It is important that you guys understand how these metrics work, even though we are using sklearn and its performance and its scoring functions to do this. sklearn has been wrong in the past. For me personally, there was a situation where I was actually using a performance metric to calculate something, and I couldn't make sense of why that outcome was happening. And I looked at my model, I looked at my process, I looked at my data, and I couldn't make sense of it. And it turns out I went into in sklearn, you can actually go look at the source code. You can click, that's not what I was looking for, but you can actually go to the source code here. There we are. And you can see how sklearn actually implements all of their evaluation metrics and their algorithms. And it turned out the implementation was wrong. And so I created a pull request and submitted that ticket, essentially, for that to be updated. And other people were tracking that as well. So important to understand how these things can work so that you guys can sanity check. So that's accuracy. One other thing I want to show you on sklearn is we go. So if you go into sklearn, like I said, there's different metrics that you can use for different types of problems. sklearn does a great job of laying these out for you. So they have metrics that you can use for classification. So if you have a classification problem, here is accuracy score, AUC, area under the curve. We're going to learn about what that is in this class. Average precision, you'll know what that is. Balanced precision, we're going to learn about that as well. And then some other nuanced ones. There's Breyer score, class likelihood ratios. You can create a classification report. We're going to talk about that. Confusion matrix, we touched on that just a little bit. So you can see all of these. Log loss, we're going to talk about. Jacquard score was the one that I found the issue in. Fun fact. F1 score, F beta score. So there are, we're going to talk about F1 score. We're going to talk about F beta score. There's precision recall curve. Here's our precision score. We just talked about precision today, and recall is in here as well. Recall score. So we just talked about precision. We could implement precision for this. Let's do that here. Precision score. Let's not do F1, just recall score. Let's do our precision score. Come to this for just a moment. So precision is 0.66 on this example, and our recall was 0.5. So these, while recall produced the same outcome that accuracy did in this case, you saw that we had higher precision. So these metrics, we're going to get different values for these. So you can use these for classification metrics. They also have regression metrics. Like I said, we're going to talk about different metrics that apply to different problems. So we'll also talk about some regression metrics. There's some multi-label ranking you can explore, and clustering evaluation. When we look at how to measure the quality of clusters, there's metrics that you can use for this. Distance metrics, pairwise metrics. So sklearn is a pretty good package for evaluation as you look at how to measure and quantify your machine learning models. Okay, let me stop sharing my screen in the stream and see if you guys have any questions. Or not in the, in the stream.